Hello everyone, my name is Ruixiang Zhao from Renmin University of China. Today I'm excited to present my work. SIV, Speech-Aware Video Representation Learning for Video Text Retrieval, accepted as CVPR 2026. Here is an overview of my talk. I will first introduce the background and motivation. Then I will propose the method SIV, followed by experimental results, and finally conclude with key takeaways. Video text retrieval aims to match videos with text queries. The dominant approach uses clip, which provides image and text encoders. However, since clip only handles visual and textual modalities, the audio track of videos is completely ignored. Recent works have tried to introduce audio by adding an audio encoder alongside the vision encoder. While these methods show improvements, they still face two critical challenges that limited their effectiveness. As shown in the comparison table, our SIV addresses both issues, supporting speech and early element, achieving the best performance. Let me explain the two issues in detail. Issue 1. Ineffective speech representation. Current audio encoders like Resonate 18 and AST are trained on environmental sounds. They can distinguish a dog bark from a bird chirp, but they cannot capture semantic content of human speech. In our toy examined on the left, we can see that while the sound and text embeddings are well separated by class, speech embeddings from AST are completely clustered with no class separation. Issue 2. Suboptimal vision audio fusion. The audio and visual features come from different encoders and are misaligned by design. Previous work above suggests the align before fields, but directly applying above with hard labels is problematic. As shown on the right, many video-audio pairs lack semantic correspondence. The background music may have nothing to do with visual content. Hard labels from a hard label would force the model to align these mismatched pairs, learning superior correlations. To jointly address both issues, we propose SIV, a tree-branch network for speech-aware video embedding. As shown in this framework feature, given a video with its soundtrack, SIV uses three branches. A vision branch uses clips image encoder for framing embedding. An audio branch uses ST for sound embedding following the AV-Gate baseline. And our newly introduced speech branch that converts speech to text with a whisper ASR, then encodes it using Cliff's text encoder. The audio and speech tokens are fused with vision tokens through gated cross attention. And the software above provides early vision audio alignment during training. Our first contribution is the dedicated speech branch. The key insight is simple yet effective. Instead of trying to make audio encoder understanding speech, we convert speech to text using whisper, then encode it with the Cliff's text encoder. This design has a natural advantage. The speech embeddings now lives in the same clip-based clip space as the test queries, providing nature pre-alignment for cross-model fusion. We also share parameters between speech text encoder and the query text encoder, which further reduce the modality gap. For the final video representation, we combine modalities use a single formula, the visual tokens plus the average of audio and speech tokens. This parameter-free design effectively gives the vision a larger weight. Importantly, our observation shows that learnable weights offer no improvement, validating this symbol that effective approach. Our second contribution is self-above for early vision audio element. The core idea is that instead of hard binary labels that say this video and audio match or not match, or don't match, we use IMI-band to compute soft relevance scores as supervision signals. For noise pairs where audio doesn't correspond to the visual content, IMI-band assigns a lower similarity score, effectively downweighting these problematic pairs. For semantically aligned pairs, they receive higher weights. We use Pearson distance loss to guide the network affinity metric to match the IMI-band soft labels. We choose Pearson distance because it's invariant to skew and location changes. Focusing on the relative ranking structure rather than absolute values, our observations confirms it outperforms MSE and Huber alternatives, as shown in the figure on the right. Soft above consistently outperforms hard above across all data filtering ratio, demonstrating its effectiveness. SIV achieves new SOTA performance on all 5 benchmarks. To better understand where our improvements come from, we manually categorize the MSVTTGK test queries into 4 groups based on their relevance to the sound and the speech. As shown in these 4 plots, SIV consistently outperforms PIG and both PIG and AVGate across all groups. The improvements are largest in the sound-speech related group, where both acoustic and semantic cues contribute, achieving largest gain over AVGate. This clearly demonstrates that both our speech branch and soft above works. Both our speech branch and soft above work. Our evaluation studies provide further insights. Removing either branch causes signaling drops, confirming that both are essential. For early alignment, hard above actually hurts performance compared to no alignment, while our soft above gives a clear gain. This validates that soft labels are crucial for handling noise visual audio pairs. We also confirm that early fusion significantly outperforms late fusion, and our parameter-free fusion design is optional. Learnable weights provide no benefit. An important practical consideration SIV is zero extra inference cost. Since all video features, including speech, can extract offline, the online inference time is identical to SIV. Meanwhile, SIV maintains linear computational complexity, making it scalable to large video collections. To summarize, Sieve makes three key contributions. The first speech variable embedding for clip-based retrieval using ASR plus clips text encoder. Second, soft LBAR for noise tolerant early vision audio element using image band soft labels. Third, new SOTA on all 5 benchmarks with zero extra inference cost. Our code is publicly available on GitHub. Thank you for your attention.